In 2013, a team of physicists at the Hebrew University of Jerusalem did something that should not be possible. They took 2 photons, 2 particles of light, and showed that they were quantum mechanically entangled, connected in that deep, strange way that Einstein called spooky, correlated so tightly that measuring one instantly told you something about the other. Entangled, except these 2 photons had never met. They had never interacted. They had never exchanged a single quantum of energy. And it was worse than that. These 2 photons had never existed at the same time. Photon 1 was created, measured, and destroyed. Gone. Annihilated. Only after it ceased to exist was Photon 4 born into the world. There is no moment in any reference frame in any corner of the universe where both photons are real simultaneously. And yet the correlations between them violated a Bell inequality. They passed 5 independent tests for entanglement. They were entangled across a gap in time where neither particle existed. This was not a thought experiment. It was not a press release stretched beyond its findings. It was published in Physical Review Letters, Volume 110, Article 210403, on the 22nd of May, 2013. 6 authors, led by Eli Megidish, in the lab of Haggai Eisenberg at the Reka Institute of Physics. The data was clean. The control experiment confirmed it. And the implication was staggering, because if 2 particles can be entangled across time, if a measurement made in the future can determine the quantum state of a particle that no longer exists, then something about the way we think about time is wrong. Not wrong in the soft philosophical time as a river sense. Wrong in the hard, experimental, the universe does not work the way your intuitions say it does sense. The kind of wrong that does not go away when you stop thinking about it. This is a story about that wrongness, about the experiments that revealed it, the people who predicted it, the mavericks who tested it against the advice of everyone around them, and the dead ends and breakthroughs and human tragedies that brought us to a place where the most fundamental feature of our experience, the flow of time from past to future, now has to answer for itself in a laboratory. But before we get to what happened in Jerusalem, and before we get to the Vienna experiment that preceded it by a year, we need to talk about entanglement itself, because there is an analogy that gets used everywhere, in textbooks, in YouTube videos, in popular science articles, and it is wrong. Not approximately wrong, fundamentally wrong. And until you see why it is wrong, you will not understand why temporal entanglement is so disturbing. The analogy goes like this. Imagine you have 2 gloves, a left and a right. You put them in separate boxes without looking. You ship 1 box to Tokyo and 1 box to London. When you open the box in London and see a left glove, you instantly know the box in Tokyo contains a right glove. No mystery, no spookiness. The information was determined when the gloves were packed. This is how a lot of people think entanglement works. 2 particles interact. They fly apart, carrying complementary properties, and when you measure one, you learn about the other. Correlation without mystery. The particles were just carrying hidden instructions the whole time, like a classical messenger pigeon. If this were true, entanglement would be boring. It would be completely explained by what physicists call local hidden variables. The particles would have definite properties all along. We just did not know what those properties were until we looked. No spookiness required. And for decades, that is exactly what most physicists assumed. Einstein certainly assumed it. In 1935, he and Boris Podolsky and Nathan Rosen published a paper in Physical Review arguing precisely this point. If quantum mechanics predicts perfect correlations between distant particles, they said, then either the particles had definite properties all along, or measuring one somehow instantaneously affects the other across any distance. Since that second option was absurd, obviously the particles had definite properties all along. Therefore, quantum mechanics must be incomplete. There must be hidden variables that quantum theory fails to describe. The paper landed like a bomb. Niels Bohr, the architect of the Copenhagen interpretation and quantum mechanics' most formidable defender, was so shaken that he dropped everything to write a response. He published a paper in the same journal with the same title, Can Quantum Mechanical Description of Physical Reality be Considered Complete? His argument was subtle, and to many physicists then and now, frustratingly opaque. Bohr essentially argued that the EPR authors were applying classical concepts in a context where those concepts did not apply. You cannot separate the quantum system from the measurement apparatus. The question, what are the particles' properties before measurement, is not a question that physics can meaningfully answer. Einstein was not satisfied. He was privately unhappy with the EPR paper itself, which had been primarily written by Podolsky and which Einstein felt did not capture his real objection clearly. His deeper point was not about specific measurements or specific particles. It was about what physics is supposed to do. Physics, Einstein believed, should describe an objective reality that exists independently of observation. Quantum mechanics seemed to deny this, and Einstein could not accept a theory that made reality dependent on what some observer in a distant laboratory chose to do. Einstein called the alternative spookhafte Fernwirkung, spooky action at a distance, and he meant it as a reductio ad absurdum. He was not saying entanglement was spooky. He was saying that if quantum mechanics required spooky action, then quantum mechanics was broken. This argument stood essentially unchallenged in any rigorous way for 29 years. But the reason it could eventually be challenged at all is because of a step that happened in between, a step taken by another outsider. In 1951, David Bohm published Quantum Theory through Prentice Hall, a textbook that contained, almost as an aside, a reformulation of the EPR argument using spin 1/2 particles in a singlet state. This sounds technical, but the effect was practical. Einstein's original EPR paper used continuous variables, position and momentum, which made the thought experiment beautiful, but experimentally intractable. Bohm translated it into the language of spin, up or down, a discrete binary measurement that could be performed in a laboratory with real magnets and real particles. Without Bohm's reformulation, Bell's theorem might never have been conceived, and even if it had, it could not have been tested. Bohm himself was an outsider of a different kind, an American physicist who had been hauled before the House Un-American Activities Committee during the McCarthy era, who refused to testify against his colleagues, who was arrested and subsequently denied tenure at Princeton. He eventually left the United States and spent the rest of his career in Brazil, Israel, and England, never returning to American academia. The man whose reformulation made the entire experimental program possible was exiled from the country where that program would first be carried out. And the person who finally took Einstein's challenge and turned it into a testable prediction was not a famous professor at a prestigious university. He was a working-class kid from Belfast. John Stewart Bell was born on the 28th of July, 1928, into a family where nobody had finished high school. His mother Annie, his father, his 3 siblings, they all left school around age 14 to work. That was the expectation. That was the economic reality of working-class Belfast in the 1930s and 40s. But Annie Bell had a vision for her children that went beyond the shipyards and the linen mills. She wanted them in jobs where they could, as she put it, wear their Sunday suits all week. John, known as Stewart at home, earned a different nickname early. His family called him the Prof. At 11, he decided he was going to be a scientist. He attended Belfast Technical High School because his family could not afford the grammar schools. Then Queen's University Belfast, where he earned 2 Bachelor of Science degrees, one in experimental physics in 1948 and one in mathematical physics in 1949. He completed his PhD at the University of Birmingham under Rudolf Peierls in 1956. And then, in 1960, he and his wife Mary Ross Bell, also a physicist, working on accelerator design, moved to CERN in Geneva. They both spent the rest of their careers there. Bell's day job was particle physics. Respectable, important, the kind of work that earns you a steady paycheck at one of the most prestigious laboratories in the world. But his passion, the thing that kept him up at night, was quantum foundations, the question of what quantum mechanics actually meant. At CERN, this was a hobby, not in the casual sense, in the literal, institutional sense. Bell pursued quantum foundations on evenings and holidays because it was not part of his job description. The physics establishment in the 1960s considered questions about the meaning of quantum mechanics to be philosophy, not physics, solved problems, distractions, career poison. Bell and his wife Mary worked side by side at CERN. For decades, she designed accelerator components. He ran numbers on particle collisions by day and pondered the foundations of reality by night. He was, by all accounts, a quiet and deeply passionate man, increasingly frustrated by what he saw as the profession's refusal to take its own deepest questions seriously. Late in his career, just months before his death, he published an essay called Against Measurement in the journal Physics World. It was a precise, devastating attack on the concept of measurement as a fundamental element of quantum theory. The word measurement, Bell argued, was vague, imprecise, anthropocentric, and had no business appearing in the axioms of a fundamental physical theory. He wanted a quantum mechanics that described what actually happens in the world, not just what observers would see if they looked. It was, in some ways, the manifesto of everything he had worked toward since 1964. Bell did not care about the establishment's disapproval. Working essentially alone, he published a paper that would eventually be recognized as one of the most important results in the history of physics on the Einstein-Podolsky-Rosen paradox, printed in a journal called Physics, sometimes listed as Physics Physique Physica, an obscure journal. Bell chose it because it paid its authors. What Bell proved was breathtaking in its simplicity and devastating in its implications. He showed that if you assume Einstein was right, if you assume particles carry hidden instructions that determine their properties before measurement, and if you assume that measuring one particle cannot instantaneously influence a distant particle, then the correlations between entangled particles must obey a mathematical inequality, a ceiling, a limit that no local hidden variable theory can exceed. And then he showed that quantum mechanics predicts correlations that exceed that limit. Think about what that means. If the glove analogy were correct, if entangled particles were just carrying predetermined properties like classical objects, then the correlations you would measure between them would always stay below Bell's ceiling. Always. No exceptions. It is a mathematical proof, not an approximation. But quantum mechanics says the correlations go higher, which means at least one of Einstein's assumptions must be wrong. Either the particles do not have definite properties before measurement, or measuring one does instantaneously influence the other, or both. There is no option where the universe is both local and realistic. Bell did not just challenge Einstein. He set up a test that the universe itself would have to take. But what makes Bell's story so remarkable and so unjust is what happened next. He published that paper in 1964, and for more than 4 years, almost nobody responded. The paper sat in an obscure journal, unread, uncited, ignored. The physics establishment had decided that quantum foundations was not a serious pursuit, and they were not going to change their minds, because a CERN accelerator physicist published something in a journal nobody read. The first direct response Bell received from any physicist came in February of 1969, a letter from a graduate student at Columbia University named John Clauser. Now, Bell proved that the universe must violate his inequality if quantum mechanics is correct. But he proved it on paper. Somebody had to actually go into a laboratory and check. Somebody had to build the experiment, align the optics, count the photons, and see whether the correlations between entangled particles really did exceed Bell's mathematical ceiling. And the person who did it first was John Clauser. But the story of how he got there reads like a case study in how the scientific establishment punishes original thinking. Clauser was born on the 1st of December, 1942, in Pasadena, California. His pedigree was impeccable. His father was a professor of aeronautical engineering at Caltech. His mother was Caltech's humanities librarian and the sister of Edwin Macmillan, who won the Nobel Prize in chemistry in 1951. Clauser earned his bachelor's degree from Caltech in 1964 and went to Columbia for his PhD. As a graduate student, he stumbled across Bell's 1964 paper in the library, the paper that nobody was reading, the paper that the entire physics community had decided was irrelevant philosophy. And Clauser became obsessed with it, not because he wanted to prove quantum mechanics right, because he wanted to prove Einstein right. He believed, like Einstein, that hidden variables would save local realism. He wanted to build the experiment that would vindicate the greatest physicist of the 20th century. His advisors told him to stop. The faculty at Columbia told him it would destroy his career. This was not a respectable line of research. This was not real physics. Clauser ignored them. He wrote to Bell in February 1969, and Bell, who had been waiting more than 4 years for anyone to take his work seriously, wrote back with encouragement. That same year, Clauser co-authored a landmark paper with Michael Horn, Abner Shimony, and Richard Holt, deriving what became known as the CHSH inequality. This was the experimentally testable version of Bell's theorem, a practical recipe. Build this apparatus, measure these correlations, and if the number S exceeds 2, local hidden variables are dead. In 1972, at UC Berkeley, Clauser and his graduate student Stuart Friedman built the experiment and ran it. Calcium atoms excited by ultraviolet light, producing pairs of entangled photons. Polarizers set at various angles. Coincidence counters clicking away in a basement laboratory. Months of data collection. The result was a 6.3 sigma violation of the CHSH inequality. Quantum mechanics was right. The correlations exceeded the classical ceiling by a margin that was, statistically, overwhelming. And Clauser was heartbroken. In his own words, "I was very sad to see that my own experiment had proven Einstein wrong." He had gone into the lab hoping to rescue local realism, and instead, he had helped bury it. The universe, it turned out, was not playing by Einstein's rules. You might expect the physics community to have celebrated this, a fundamental question about the nature of reality, tested and answered in a laboratory. You would be wrong. Richard Feynman at Caltech was reportedly highly offended by the experiment. He called it tantamount to professing a disbelief in quantum physics, as if the experiment were an insult to the theory it confirmed. When Clauser reconnected with faculty at Columbia, their response was blunt. "We told you so. Now stop wasting money and go do some real physics." Clauser never secured a traditional academic professorship. After stints at Lawrence Livermore and UC Berkeley, he ended up operating as a one-man consultancy, JF, Clauser and Associates, in Walnut Creek, California. The man who performed the first experimental test of the most important theorem in quantum foundations spent decades on the margins of the field he helped create. But Clauser's experiment had a loophole, a technical gap that left a sliver of room for local hidden variables to survive. His polarizer settings were fixed before each run. In principle, the photons, or some unknown physical process, could have known in advance what settings would be used and conspired to produce the observed correlations. This is called the locality loophole. To close it, you would need to change the polarizer settings while the photons were already in flight, faster than any signal could travel between the two detectors. And that is exactly what a young French physicist decided to do. Alain Aspect was born on the 15th of June, 1947, in Agen, France. After earning his physics aggregation in 1969, he spent 3 years teaching in Cameroon as an alternative to compulsory military service. Think about that. 3 years in equatorial Africa, teaching physics, far from any major research laboratory. And during those 3 years, Aspect read everything he could find about Bell's theorem. He conceived his entire experimental program while teaching undergraduates in Cameroon. When Aspect returned to France in 1974, he sought out John Bell to discuss his plans. Bell's first question was not about the physics. It was not about the experimental design or the predicted correlations or the statistical analysis. Bell's first question was, "Do you have a permanent job?" Because Bell knew what happened to people who worked on this. He had watched the field he essentially created treat its practitioners as outcasts. He wanted to make sure this young physicist would not be destroyed by the work. Aspect did have a permanent position, and between 1980 and 1982, he conducted 3 progressively more rigorous experiments at the Institut d'Optique in Orsay. The first 2 improved on Clauser's measurements with vastly better photon sources and 2-channel polarizers. But the third was the one that changed everything. In December of 1982, working with John Dalibard and Gerard Roger, Aspect built a setup where the polarizer settings were switched by acousto-optical devices every 10 nanoseconds while the photons were in flight. The two polarizers were separated by 12 meters, and light needs about 40 nanoseconds to cross that distance. The settings changed faster than any signal. Even a light speed signal could communicate between the two sides. The result was S equals 2.697 plus or minus 0.015. The classical limit is S less than or equal to 2. Aspect's experiment blew past it, matching the prediction of quantum mechanics with extraordinary precision. And this time, the locality loophole was closed. There was no way for the particles to have conspired in advance, because the measurement settings did not exist until after the particles were already on their way. Local realism was not wounded, it was dead. The universe does not have definite, predetermined properties that exist independently of measurement. Or if it does, then measurements on one particle do instantaneously influence distant particles in a way that cannot be explained by any local mechanism. Or both. Bell's inequality was violated. Einstein's program had failed. But here is where the story takes its most unexpected turn. Because proving that entanglement is real, proving that Bell inequalities are violated, proving that the universe is not locally realistic, all of that was just the beginning. It answered the question of whether entanglement was genuine. It did not answer the question of what entanglement is. It did not explain how two particles with no common cause and no physical connection could be correlated in ways that exceed any classical possibility. And it certainly did not prepare anyone for what would come next. Because if entanglement between particles separated in space was disturbing, entanglement between particles separated in time, particles that never coexisted in the same universe at the same moment, was going to be something else entirely. The man who first saw that possibility was trained by Einstein's own collaborator, and his life story is one of the most extraordinary in all of 20th century physics. Asher Perez was born on the 30th of January 1934 in Beaulieu-sur-Dordogne, France. His birth name was Aristide Pressman. The name Asher was not on the French government's list of permissible given names, so his parents, Shlomo and Shulamit Pressman, Jewish émigrés from Lemberg, now Lviv in Ukraine, registered him as Aristide. His father was a Polish electrical engineer. His mother had come to France seeking a life away from the anti-Semitism of Eastern Europe. They did not find it. Shortly after Asher's birth, the family was deported to Poland. They managed to return to France just before the Second World War began, but the fall of Paris changed everything. Their Jewish identity was exposed by local anti-Semites. Extortion followed. Asher's father joined the French resistance, while his mother took young Asher into hiding. A child and his mother concealed from the people who would have sent them to the camps, while his father fought in secret against the occupation. Perez wrote about these experiences decades later in a memoir he titled "I Am the Cat Who Walks by Himself," after the Kipling story. He posted it on the Arxiv preprint server in April of 2004, just months before his death. It is a document worth reading, not just for what it tells you about the man, but for what it tells you about the kind of mind that could emerge from that kind of childhood. A mind that learned early that the world does not owe you safety, that official stories are not always true, and that survival sometimes requires seeing what others refuse to see. The family was reunited after the war and immigrated to Israel in 1949. Peres enrolled at the Technion, the Israel Institute of Technology, in 1952. His father, a practical man, persuaded him to study mechanical engineering. There were no jobs for physicists, he said. Study something useful. There is a wonderful story from those years. In one of his mathematics classes, Peres found and pointed out an embarrassing error in one of the professor's proofs. The professor's response was to promise Peres the highest grade in the course, on the condition that he never attend the lectures again. His first paper in theoretical physics was written while he was still a second-year undergraduate. It was recommended for publication in Comptes Rendus by Louis de Broglie himself, one of the founders of quantum mechanics, in 1954. A second-year engineering student publishing theoretical physics on the recommendation of a Nobel laureate. This was not a normal trajectory. Peres earned his PhD in 1959 from the Technion, and his doctoral advisor was Nathan Rosen. That name should ring a bell. Nathan Rosen was the R in EPR. Einstein, Podolsky, and Rosen, the 1935 paper that started everything. The paper that identified entanglement as the central puzzle of quantum mechanics. Peres was trained by a man who had sat across the desk from Albert Einstein and debated the foundations of reality with him. Think about that intellectual lineage for a moment. Einstein identifies the puzzle. His collaborator Rosen trains Peres, and Peres, decades later, proposes the most radical extension of that puzzle, one that Einstein could not have imagined. The chain from the 1935 EPR paper to the 2012 and 2013 experiments runs directly through Asher Peres and his doctoral advisor. Peres spent his entire career at the Technion, appointed Distinguished Professor of Physics in 1988. His contributions to quantum information theory were foundational. In 1993, he was one of the 6 authors of the landmark quantum teleportation paper, published in Physical Review Letters with Bennett, Brassard, Crapo, Jossa, and Wouters. 6 authors, 6 fathers of quantum teleportation, and Peres was among them. He developed the Peres-Horodecky criterion for detecting entanglement, a mathematical test that works by checking whether reversing the direction of time for one of 2 particles produces negative probabilities. If it does, the particles must be entangled. There is something almost prophetic about the fact that Peres's entanglement criterion involves reversing time, given what he would later propose. His textbook, Quantum Theory, Concepts and Methods, published by Kluwer in 1993, was called the modern successor to von Neumann's mathematical foundations of quantum mechanics. And in a move that tells you everything about his personality, Peres gave the uncertainty principle only a single entry in the book's index. The page number it pointed to was the index page itself. His signature philosophical statement was 5 words long. Unperformed experiments have no results, not a platitude, a precise philosophical position. If you have not measured something, you cannot assign it a definite value. The measurement is not revealing a pre-existing fact. It is participating in the creation of the fact. When a reporter asked Peres whether quantum teleportation could teleport the body as well as the soul, he replied, "No, not the body, just the soul." In 2000, Peres published a paper that would become his most radical contribution. Delayed choice for entanglement swapping in the Journal of Modern Optics, volume 47, pages 139 through 143. It was a sole author paper submitted to the Arxiv on the 11th of April, 1999. To understand what Perez proposed, you need to know about entanglement swapping. The concept was first laid out in 1993 by Marek Zukowski, Anton Zeilinger, Michael Horn, and Arthur Eckert in Physical Review Letters. The idea is startling, but the protocol is precise. You start with two completely independent pairs of entangled photons. Pair 1 consists of photons 1 and 2, entangled with each other. Pairs 2 consists of photons 3 and 4, entangled with each other. Photons 1 and 4 have never interacted. They have no common source, no shared history, no physical connection of any kind. Now you take the middle photons, 2 and 3, one from each pair, and you perform a special joint measurement on them called a Bell state measurement. You project them onto one of the 4 maximally entangled Bell states. And when you do this, something extraordinary happens. Photons 1 and 4, the outer photons that have never met, become entangled. The entanglement has been swapped from the original pairs to a new pair that shares no common origin. This was experimentally demonstrated in 1998 by Jian-Wei Pan, Dick Baumeister, Harold Weinfurter, and Anton Zeilinger at the University of Innsbruck. Published in Physical Review Letters on the 4th of May, 1998. Entangling photons that never interacted. It was strange, but at least all 4 photons existed at the same time. All 4 were in the laboratory simultaneously. The measurement on photons 2 and 3 happened while photons 1 and 4 were still available. You could draw a line through the experiment at any given moment and find all 4 photons present and accounted for. Jian-Wei Pan, incidentally, would go on to become one of the most important figures in quantum physics. He returned to China and led the team that launched the Messier satellite, built the Beijing-Shanghai quantum backbone, and established China as the world leader in quantum communication. The student who helped demonstrate entanglement swapping in an Innsbruck laboratory in 1998 was, within 2 decades, overseeing a national quantum infrastructure spanning thousands of kilometers. The progression from tabletop proof of concept to global technology happened within a single career. What Perez did in his 2000 paper was combine entanglement swapping with an idea from John Archibald Wheeler called delayed choice. Wheeler had proposed in 1978 that in a double-slit experiment, you could delay the choice of whether to observe which path information or interference until after the particle had already passed through the slits. The choice made after the fact would determine the nature of the result. Wheeler imagined a cosmic version, a photon from a distant quasar gravitationally lensed around a galaxy, billions of light years away, where our choice today of how to detect the photon would determine whether it traveled as a wave or particle billions of years ago. Perez took Wheeler's delayed choice concept and applied it to entanglement swapping. In his thought experiment, Alice and Bob each have 1 photon from their respective entangled pairs. They measure their photons and record the results. Done. Their photons are measured and destroyed. The data is written down. Then, at a later time, a 3rd observer, Eve, receives the remaining 2 photons, 1 from each pair, and chooses whether or not to perform the Bell state measurement that would swap the entanglement. If Eve performs the measurement, Alice and Bob's already recorded data when sorted by Eve's results, reveals entanglement between their photons. If Eve does not perform the measurement, no entanglement is visible. Eve's choice, made after Alice and Bob's photons have been measured and destroyed, determines whether those photons were entangled. Peres's own words captured the vertigo of this idea. If we attempt to attribute an objective meaning to the quantum state of a single system, curious paradoxes appear. Quantum effects mimic not only instantaneous action at a distance, but also, as seen here, influence of future actions on past events, even after these events have been irrevocably recorded. Read that sentence again. Influence of future actions on past events, even after these events have been irrevocably recorded. Peres was not speculating about philosophy. He was describing a specific experimental prediction of standard quantum mechanics. No new physics required, no exotic interpretations, just the regular textbook quantum formalism taken seriously, predicting that a choice made in the future could determine whether particles in the past were entangled. And pay attention to the word mimic. Peres chose that word carefully. The effects look like retroactive influence. They walk like retroactive influence, and they talk like retroactive influence. But Peres was too careful a thinker to claim they are retroactive influence. He said, mimic. The distinction matters, and we will come back to it. But here is something that needs to be said clearly, because it is the misconception that causes the most damage when people encounter these experiments for the first time. This does not mean you can send messages back in time. The reason is subtle but absolute. When Alice and Bob measure their photons before Eve makes her choice, their individual results are perfectly random, 50-50, completely indistinguishable from noise. There is nothing in Alice's data and nothing in Bob's data that reveals whether Eve will later perform the entanglement swap or not. The correlations between Alice's and Bob's results only become visible when you take Eve's results and use them to sort Alice and Bob's data into subsets. In the subset where Eve found Bell's state phi- for her two photons, Alice and Bob's results show entanglement correlations. In the subset where Eve performed a different measurement, they do not. But you need Eve's data to do the sorting, and Eve's data can only reach Alice and Bob through a classical communication channel, a phone call, an email, a letter, something limited to the speed of light. Without that classical data, Alice and Bob cannot extract any meaningful pattern from their results. The correlations are invisible without the key, and the key cannot travel faster than light, much less backward in time. So no time travel, no faster than light signaling, no grandfather paradoxes. The no communication theorem, a rigorous mathematical proof within quantum mechanics, guarantees that entanglement alone cannot transmit information. Period. What these experiments do is something more subtle and, in some ways, more disturbing. They show that the question of whether two particles were entangled, a question about the past, can depend on a measurement made in the future. The past is not being changed, but what we can say about the past, what categories it falls into, what correlations exist in the records, that depends on something that has not happened yet. And that raises a question that physics has not answered. If the correlations are real, if they violate Bell inequalities, if they cannot be explained by predetermined hidden variables, then what is the status of the past? Is it fixed and definite and waiting for us to discover it? Or is it in some precise and experimentally demonstrable sense, open. Asher Perez did not live to see his thought experiment tested. He died on the 1st of January 2005 in Haifa at the age of 70, 7 years before the first experimental realization. The experiment that brought Perez's proposal to life was conducted by a team in Vienna led by Anton Zeilinger. The paper was published as Experimental Delayed Choice Entanglement Swapping in Nature Physics, Volume 8, pages 479 through 484. On the 22nd of April 2012, the authors were Xiao Song Ma, Stefan Zotter, Johannes Koffler, Rupert Ursin, Thomas Genowain, Czaslaw Bruckner, and Anton Zeilinger, all affiliated with the Institute for Quantum Optics and Quantum Information at the Austrian Academy of Sciences and the Vienna Center for Quantum Science and Technology. Anton Zeilinger is one of those rare physicists whose experimental achievements read like a highlight reel of an entire field. Born on the 20th of May, 1945, in Ried im Innkreis, Upper Austria. Physics and mathematics at the University of Vienna. PhD in 1971 on neutron depolarization in dysprosium single crystals under Helmut Rausch. A Fulbright Fellowship at MIT's Neutron Diffraction Laboratory, working with C.G. Schull, who would go on to win the 1994 Nobel Prize. Professorships at Vienna University of Technology, Technical University of Munich, the University of Innsbruck, and then back to the University of Vienna in 1990. His group demonstrated quantum teleportation experimentally in 1997, entanglement swapping in 1998, GHZ state entanglement in 1990. Entanglement distributed over 144 kilometers between the Canary Islands between 2006 and 2010. The first quantum encrypted intercontinental video call between Vienna and Beijing using the Messier satellite in September 2017. He named his sailboat 42 after the answer to life, the universe, and everything in Douglas Adams's Hitchhiker's Guide to the Galaxy. On the 4th of October 2022, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics jointly to Alain Aspect, John Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Clauser, who had been told the work would destroy his career, who had never secured a permanent academic professorship, who had spent decades as an independent consultant in Walnut Creek, California, received the Nobel Prize 50 years after his first experiment. His collaborator on that first experiment, Stuart Friedman, had died in 2012. He could not share the award, and John Bell, whose theorem made all of it possible, whose name appeared in the Nobel citation itself, had been dead for 32 years. He died suddenly on the 1st of October 1990 in Geneva of a cerebral hemorrhage at the age of 62. He had reportedly been nominated for the Nobel Prize that year. The nominations are sealed for 50 years, so we cannot officially confirm this, but it is widely reported. What we can confirm is that the prize eventually went to the experimentalists who confirmed his theorem, Bell's theorem. Bell's inequality, Bell's name on every paper, every textbook, every experiment, but no phone call from Stockholm. So Zeilinger had the track record, the resources, the team, and the institutional support. And in 2012, his group set out to realize what Perez had proposed 12 years earlier. The Vienna experiment had 3 critical design elements that made it definitive. The first was an optical delay. In Perez's original proposal, the key feature was that the entanglement swapping measurement happens after the outer photons have already been measured. The Vienna team enforced this with fiber optics. Victor's photons, the ones that would undergo the Bell state measurement, were routed through 104 meters of optical fiber, introducing a delay of approximately 520 nanoseconds. Meanwhile, Alice's and Bob's photons traveled through only 7 meters of fiber, about 35 nanoseconds. This meant photons 1 and 4 were measured roughly 485 nanoseconds before Victor even received his photons. The temporal ordering was unambiguous. The second element was active random switching. A quantum random number generator controlled a high-speed, tunable bipartite state analyzer in real time, ensuring Victor's choice of measurement was genuinely random and could not have been predicted by any physical process at the time Alice and Bob measured their photons. This was not a predetermined setting. It was a choice generated by quantum randomness itself, made after the outer photons were already gone. The third element was time-like separation. Victor's choice and measurement occurred in the absolute future of Alice's and Bob's measurements, not just later in the laboratory clock, later in every reference frame. There is no way to boost into a frame where Victor's measurement happens before Alice's and Bob's. The temporal ordering is Lorentz invariant. It is a fact of space-time geometry, not a feature of any particular observer's perspective. Victor had 2 options. He could perform a Bell state measurement, projecting his 2 photons onto entangled states, which would swap the entanglement to photons 1 and 4. Or he could perform what the team called a separable state measurement, projecting onto product states, which would not create any entanglement between the outer photons. The results were exactly what quantum mechanics predicted. When Victor performed the Bell state measurement, the correlations between photons 1 and 4, photons that had already been measured and registered before Victor made his choice, showed entanglement. When Victor performed the separable state measurement, those same photon pairs showed no entanglement, only classical correlations. Whether photons 1 and 4 were entangled or separable was determined by a choice made after they had already been measured and destroyed. The authors described this as quantum steering into the past. They explicitly stated that their experiment was the first realization of Perez's Gedanken experiment with active, random, delayed choice, and they extended the conceptual framework of Wheeler and Bohr into territory neither had imagined. Some registered phenomena do not have a meaning unless they are put in relationship with other registered phenomena. Sit with that for a moment. The measurement results of photons 1 and 4, written down, recorded, finished, do not have a definite meaning, do not fall into the category of entangled or not entangled until Victor makes his choice and his data is compared with theirs. The past is not being changed. The records are not being rewritten. But the interpretation of those records, the physical category they belong to, depends on something that happens later. And then, 1 year after Vienna, the Hebrew University team did something even more extreme. The Vienna experiment was stunning, but it had a feature that if you squinted hard enough, let you hold on to a vestige of normalcy. In the Vienna setup, all 4 photons existed at the same time, briefly, for those 520 nanoseconds, while Victor's photons were traveling through the fiber delay. All 4 photons were somewhere in the apparatus. Photons 1 and 4 had already been measured, yes, and their quantum states had been projected onto definite outcomes, but the photons had at least coexisted, however briefly, in the same temporal window. You could, if you were determined to preserve your intuitions, argue that whatever correlations arose had their origin in that brief window of coexistence. The Megiddish experiment closed that door. The team at the Hebrew University of Jerusalem, led by Haggai Eisenberg, designed an experiment where the 2 entangled photons would have 0 temporal overlap, not brief overlap, not marginal overlap. 0. Photon 1 would be created, measured, and destroyed before photon 4 even came into existence. Eisenberg is an associate professor at the Reicha Institute of Physics, a graduate of the Technion and the Weizmann Institute, who completed a postdoctoral fellowship at UC Santa Barbara before joining Hebrew University in 2005. The Reicha Institute is named after Giulio Reicha, an Italian-born physicist who immigrated to Israel and is called the father of theoretical physics in the country. So there is another thread of connection running through this story, another line linking the institutions and the people. Peres spent his career at the Technion. Eisenberg was trained there. The experiment that confirmed Peres's prediction was carried out by a scientist educated in the same tradition at a university in the same city where Peres had imagined it. The experimental protocol had 5 steps, and the temporal ordering was strict. Step 1. A beta barium borate crystal, pumped by a laser, produces an entangled pair of photons via spontaneous parametric down conversion. These are photons 1 and 2. They are born entangled, correlated in polarization in the way that Bell showed cannot be explained by hidden variables. Step 2. Photon 1 is measured. Its polarization is detected, recorded, and photon 1 ceases to exist. It has been absorbed by the detector, gone, irreversibly. Step 3. Only now, after photon 1 has been destroyed, does the same crystal produce a second entangled pair, photons 3 and 4, born after photon 1's death. There is no moment in any frame of reference where photon 1 and photon 4 coexist. Step 4. Photons 2 and 3, one from each pair, are subjected to a Bell state measurement. This is the entanglement swapping step. Photon 2 has been waiting, stored in the apparatus, since step 1. Photon 3 was just born in step 3. The Bell state measurement projects them onto a joint entangled state, and in doing so, swaps the entanglement to photons 1 and 4. Step 5. Photon 4 is measured. Now stop and think about the timeline. Photon 1 is born, measured, and destroyed. Then photon 4 is born and measured. The 2 photons whose entanglement is being tested have lifetimes that do not overlap at all. Their existence is sequential, not simultaneous. They are separated not just by space, but by a gap in time during which neither particle exists. And yet, when the team performed full quantum state tomography on the joint state of photons 1 and 4, reconstructing the density matrix of the 2-photon system, they found entanglement. They did not rely on a single criterion. They tested for entanglement using 5 independent measures, any one of which would be considered sufficient by the standards of the field. First, fidelity with a maximally entangled state, exceeding the 0.5 threshold. Second, concurrence, which was non-zero. Third, the Perez-Horodecky partial transpose criterion, which returned a negative eigenvalue. This is the criterion that Perez himself developed, the one that checks whether reversing time for one particle produces negative probabilities. The man who proposed the experiment had also invented one of the tools used to verify its results. Fourth, violation of an EPR steering inequality. Fifth, violation of a CHSH Bell inequality, with S greater than 2. All 5 criteria confirmed entanglement between photons 1 and 4, photons that never shared a single moment of existence. Haggai Eisenberg's summary was precise and devastating in its understatement. There is no moment in time in which the 2 photons coexist, so you cannot say that the system is entangled at this or that moment. Read that again. You cannot say the system is entangled at this or that moment. The entanglement does not exist at a point in time. It exists as a correlation structure in the data, visible only when the records of all 4 measurements are brought together and compared. It transcends the usual temporal framework entirely. The team ran a control experiment to confirm their result was genuine. They introduced temporal distinguishability between the projected photons, a technical modification that should destroy the entanglement swapping protocol if it is working as quantum mechanics predicts. And indeed, the entanglement disappeared. The control worked. The main result was real. The paper was published in Physical Review Letters on the 22nd of May, 2013. The arXiv preprint had been submitted back in September 2012 with a slightly different title. The preprint was called Entanglement Between Photons That Have Never Coexisted. The journal version was Entanglement Swapping Between Photons That Have Never Coexisted. A small difference, but worth noting for precision. Now think about where we are. Einstein in 1935 was disturbed by the idea that measuring a particle here could instantly affect a particle there. Spooky action at a distance. He used that spookiness as evidence that quantum mechanics must be incomplete. Bell in 1964 proved that the spookiness was inescapable. Clauser in 72 and Aspect in 82 confirmed it experimentally. The universe really is non-locally correlated in ways that no hidden variable theory can explain. But all of those experiments involved particles separated in space. The 2 photons in Aspect's experiment were 12 meters apart. The photons in later tests were separated by hundreds of meters, then kilometers, then using the MISHIS satellite over 1,200 kilometers. Spooky action at a distance. The distance kept growing, but it was always distance, spatial separation. The particles existed at the same time. The Medjugorje experiment introduced a different kind of separation, not distance, duration. The particles were separated in time, and not just separated by a gap during which both existed, separated by a gap during which neither existed. The causal void between the death of one photon and the birth of the other, as Elise Krull described it in Aeon magazine. If Einstein found correlations across space disturbing, correlations across a temporal void where neither correlated particle exists would have been something else entirely. So what does this tell us about time? This is the question that makes physicists uncomfortable. Not because the experiments are ambiguous. The data is clean, replicated, confirmed by multiple independent criteria, published in the highest tier journals. The experiments are not the problem. The problem is that our best theoretical frameworks disagree about what the experiments mean. Let me start with what we can say for certain. We can say that temporal entanglement does not allow time travel or faster than light communication. This is mathematically proven by the no communication theorem, which shows that the reduced density matrix of any subsystem is independent of measurements performed on other subsystems. In plain language, Alice's measurement results, taken by themselves, look completely random regardless of what Victor does in the future. The correlations between Alice's and Bob's data only emerge when you condition on Victor's outcomes. And learning Victor's outcomes requires ordinary, speed of light limited, classical communication. No information travels backward. We can also say that the classical intuition about the past being fixed and definite, the intuition that events that have already happened have a single, determinate character that cannot be changed, needs serious qualification. The Ma et al. Paper in Nature Physics was careful about this. They wrote, "There is never a paradox if the quantum state is viewed as no more than a catalogue of our knowledge." On this reading, Victor's measurement does not change the past. It changes our ability to categorize already recorded data. The records do not change. The meaning of the records changes, but that resolution has a cost. If the quantum state is just a catalogue of knowledge, then it is not a description of objective physical reality. It is a bookkeeping tool. And that means physics, at its deepest level, is not telling us what the world is like. It is telling us how to organize our experiences. A lot of physicists find that deeply unsatisfying. The alternative is to take the quantum state seriously as a description of reality. And if you do that, temporal entanglement becomes much harder to explain. The most direct confrontation with temporal entanglement comes from the retrocausality camp. These are physicists who argue that causal influences can, in some precise sense, propagate backward in time, not in the science fiction sense, not in the send a message to your past self sense, in the sense that an experimenter's choice at a later time can be correlated with physical variables at an earlier time, and this correlation is not due to a common cause in the past. The idea has a longer pedigree than most people realize. In 1947, the French physicist Olivier Costa de Beauregard proposed that entangled particles remain correlated by means of what he called a zigzag through space-time, a retarded wave going forward in time from the source, and an advanced wave going backward in time from the measurement. His supervisor, Louis de Broglie, forbade publication. The idea was too radical, too far outside the mainstream, too dangerous for a young physicist's reputation. Sound familiar? Decades later, it would be reconsidered by serious researchers working on quantum foundations. Hugh Price, a philosopher of physics at Cambridge and Bonn, argued in a 2012 paper in Studies in History and Philosophy of Modern Physics that any quantum theory that treats the quantum state as real and the quantum world as time-symmetric must allow retrocausal influences. Ken Wharton, at San Jose State University has developed formal retrocausal models. Together, in a 2021 paper in Foundations of Physics, Price and Wharton proposed that entanglement arises from what they called constrained retrocausal collider bias, a statistical phenomenon where conditioning on a common effect creates correlations between its causes, even when those causes have no direct connection. This is a known statistical effect in classical probability theory. Price and Wharton's claim is that the quantum correlations in delayed choice experiments might be an instance of this same effect, operating through the time-symmetric structure of physics. Perhaps the interpretation that handles temporal entanglement most naturally is the two-state vector formalism developed by Yakir Aharonov, Peter Bergman, and Joel Lebowitz in 1964. In this framework, a quantum system at any given time is described not by a single quantum state, but by two. One state evolves forward in time from the past preparation. The other evolves backward in time from the future measurement. The full description of reality at any moment requires both. As Lev Weidman at Tel Aviv University puts it, information given by forwards evolving quantum states is not complete. Both past and future measurements are required for providing complete information. If you take this seriously, then the idea of temporal entanglement becomes almost obvious. Of course, a future measurement contributes to the physical description of a past event. The formalism was designed to incorporate exactly that kind of influence. The Megadish experiment is not a paradox within the two-state vector formalism. It is a confirmation of the formalism's central claim. But other interpretations handle it differently, and each one extracts a different moral from the same experimental data. The Copenhagen interpretation, in its many variants, dissolves the puzzle by denying that the quantum state describes objective reality. Victor's measurement updates the available information, allowing previously random data to be properly categorized. No physical influence travels backward. Nothing about the past changes. The quantum state is epistemic, not ontic. Problem solved at the cost of abandoning the idea that physics tells us what reality is actually like. The many worlds interpretation says all outcomes of Victor's measurement occur in different branches of the universal wave function. In some branches, photons 1 and 4 are entangled. In others, they are not. All branches coexist. The apparent delayed choice is just a reflection of which branch the observer happens to inhabit. No retrocausation required, at the cost of accepting an infinite proliferation of unobservable parallel universes. The transactional interpretation proposed by John Cramer in Reviews of Modern Physics in 1986 describes quantum events as a handshake between a retarded offer wave traveling forward in time and an advanced confirmation wave traveling backward in time. The transaction that constitutes a quantum event is atemporal. It does not happen at a particular moment. It is a four-dimensional structure in space-time. Temporal entanglement fits naturally because the transaction was never restricted to a single moment in the first place. Cubism, the quantum Bayesian interpretation, treats the wave function as an agent's personal beliefs about future measurement outcomes. Temporal entanglement is unproblematic because no objective entanglement is created or destroyed at any time. Victor updates his beliefs, which allow him to reinterpret earlier data. Nothing weird happens in the physical world. The weirdness is in our expectations, not in reality. And here is where the situation stands in 2026. Each internally consistent, each capable of accommodating the experimental results, none definitively ruled out. The experiments do not tell us which interpretation is correct. They tell us that the universe produces correlations that violate Bell inequalities across time, between particles that never coexisted, and that these correlations depend on future measurements. What that means for the nature of time depends on which interpretive framework you adopt, and the choice between frameworks is, at present, a matter of philosophical commitment rather than experimental evidence. The debate is not academic. In 2019, David Glick argued in a philosophy paper that we should take time-like entanglement relations seriously as genuine physical relations between events at different times. If he is right, this has implications for the metaphysics of time. If events at different times can be entangled, can be connected by physical relations that violate Bell inequalities, then those events must, in some sense, all be real. A photon that no longer exists and a photon that does not yet exist cannot be physically related unless the times at which they exist are, in some framework, equally real. This is the block universe, eternalism, the view that past, present, and future all exist as parts of a four-dimensional space-time structure with no privileged now. If temporal entanglement is a real physical relation, it is evidence for the block universe. But in 2024, John Clerfel-Emjelve published a direct rebuttal in Studies in History and Philosophy of Science. He argued that the correlations in delayed choice entanglement swapping experiments are artifacts of post-selection, not evidence of genuine temporal non-locality. The entanglement, on his reading, is ordinary space-like entanglement between the photons that undergo the Bell state measurement. The appearance of temporal entanglement is a statistical illusion created by sorting the data after the fact. The experimental results are not disputed. Both Glick and Emjelve agree on what the laboratories found. They disagree on what it means. And that disagreement is not a failure of physics. It is physics working exactly as it should at the frontier, where the data has outpaced our conceptual frameworks, and the experiments are posing questions that our interpretations are not yet equipped to answer. Asher Paris, in his 2000 paper, saw this coming. He closed with a sentence that feels, 2 decades later, like a warning and an invitation. He said that if we attempt to attribute an objective meaning to the quantum state of a single system, curious paradoxes appear. The paradoxes mimic influence of future actions on past events. The word mimic was doing critical work. Perez was not claiming the future influences the past. He was not claiming it does not. He was saying that quantum mechanics, taken at face value, produces results that look exactly like retroactive influence, and that the question of whether they are retroactive influence depends on a question quantum mechanics itself does not answer. What is the quantum state? Perez died on the 1st of January 2005. The Vienna paper, published 7 years after his death, explicitly stated, motivated by Perry's radical idea, we report the first realization of Perry's Gedanken experiment. The Hebrew University experiment followed 8 years after his death. The man who was hidden as a child in wartime France, trained by Einstein's collaborator, and who proposed that entanglement could transcend time itself, did not live to see the experiments that confirmed his most extraordinary prediction. There is a cruel symmetry in that. Pairs proved that entanglement could bridge the gap between the past and the future, but he could not bridge the 7-year gap between his proposal and its confirmation. The man who showed that particles do not need to share a moment in time to be correlated did not share a moment in time with the data that proved him right. And Bell, who started everything by showing that the universe is not locally realistic, whose theorem made entanglement swapping meaningful, whose inequality is the standard by which entanglement is verified, died in Geneva in 1990, alone except for the suddenly urgent phone calls from colleagues. He was 62. There is a road at CERN named Route Bell. There is a street in Belfast's Titanic Quarter called Bell's Theorem Crescent. The John Stewart Bell Prize has been awarded since 2008, but Bell never received the phone call from Stockholm, and the prize that eventually recognized his work went to the experimentalists who tested his theorem, not to the theorist who proved it. But these experiments did not appear out of nowhere. Paris's 2000 proposal was brilliant, but it was built on a conceptual foundation laid by someone else, someone who spent decades asking a question so simple that most physicists thought it was beneath them. The question was this: if a quantum event depends on how you measure it, and you do not choose how to measure it until after the event has already occurred, then what happened? The person who asked that question was John Archibald Wheeler, and he asked it in a way that still makes physicists uncomfortable almost 50 years later. Wheeler was born in 1911 in Jacksonville, Florida, and died in 2008 in Hagerstown, Maryland, at the age of 96. Between those dates, he lived one of the most extraordinary careers in the history of physics. He worked with Niels Bohr on the liquid drop model of nuclear fission. He coined the term black hole. He mentored Richard Feynman as a PhD student at Princeton. He was, by any standard, a giant. But his most lasting contribution may be a thought experiment he first proposed in 1978, published in an essay in Mathematical Foundations of Quantum Theory, and expanded in his 1984 piece, Law Without Law, in the volume Quantum Theory and Measurement. The experiment is called the Delayed Choice Experiment, and it works like this. In a standard double-slit setup, a particle passes through two slits and produces an interference pattern on a detector screen, proving it behaved as a wave. But if you place detectors at the slits to determine which path the particle took, the interference pattern disappears, and you get two bands, proving it behaved as a particle. Wave or particle depends on whether you look. Wheeler's twist was timing. What if you wait until after the particle has already passed through the slits to decide whether to observe which path information? The particle has already done whatever it did. It has already passed through the slits as a wave, as a particle, as whatever it is. And now you choose. Observe the path and you find a particle. Do not observe the path and you find interference. Your choice, made after the fact, determines what the particle did. This was confirmed experimentally in 2007 by Vincent Jacques, Alain Aspect, and their colleagues, published in Science. The delayed choice is real. The choice made after the event determines the character of the event. But Wheeler took it further. He imagined a cosmic version, a photon emitted by a quasar billions of light years away. The light passes a massive galaxy, which gravitationally lenses it, splitting the path into two routes around the galaxy, like light going through a cosmic double slit. The photon has been traveling for billions of years, and now Today, you choose how to detect it. You can set up your telescope to observe interference, in which case the photon traveled both paths as a wave. Or you can set up your telescope to determine which path it took, in which case it traveled one path as a particle. Wheeler's own words capture the vertigo. There is an inescapable sense in which we, in the here and now, by a delayed setting of our analyzer, have an unavoidable influence on what we have the right to say about what we call the past, not the recent past. The past measured in billions of years. Your choice today in your observatory determines something about what a photon did before the Earth existed. Think about the scale of that claim. A photon that left a quasar when the universe was young. That has been traveling through empty space for longer than the solar system has existed, does not have a definite history until you choose how to detect it. The history is not sitting there waiting to be uncovered. It is, in some sense, brought into being by the measurement. The past is not past until it is observed. And Wheeler went further still. He proposed a vision of reality he called the participatory universe. No phenomenon is a real phenomenon until it is an observed phenomenon. The universe is not a machine running on fixed rails from past to future. It is something we participate in creating retroactively through our observations. His slogan for this worldview was "It from bit." Information, he argued, is the fundamental building block of physical reality. Every particle, every field, every force derives its existence from the answers to yes or no questions, binary choices, bits. The physical world, in Wheeler's view, is not made of matter or energy at its deepest level. It is made of information. And information requires an observer to give it meaning. This was not mysticism. Wheeler was not invoking consciousness or human specialness. He was making a claim about the logical structure of physics. The equations of quantum mechanics are, at bottom, rules for calculating probabilities of measurement outcomes. The outcomes do not exist until the measurement occurs. If you take this seriously, all the way down, then the universe is not a collection of things. It is a network of observations, a web of information. And the things we call physical objects are stable patterns within that web. Wheeler's delayed choice experiment dealt with a single particle and the question of wave or particle. Perez's delayed choice entanglement swapping dealt with pairs of particles and the question of entangled or separable. The conceptual lineage is direct. Wheeler showed that the character of a past event could depend on a present choice. Perez showed that the relationship between past events, whether they were correlated in that deep quantum mechanical way that Bell had proven could not be faked, could depend on a future choice. Wheeler opened the door. Perez walked through it, and the Vienna and Jerusalem experiments proved the room on the other side was real. In 2017, Zeilinger's group pushed Wheeler's cosmic idea into the laboratory. They conducted what they called a cosmic Bell test, published in Physical Review Letters, where the measurement settings for a Bell experiment were determined not by a random number generator, but by the light from stars. Photons from stars over 600 light-years away, emitted before the experimenters were born, before the experiment was conceived, were used to set the polarizer angles. If some cosmic conspiracy were trying to predetermine the settings, it would have needed to start manipulating the starlight 6 centuries ago, long before anyone knew what a Bell test was, long before anyone knew what a photon was. the Bell inequality was still violated. Whatever was producing the correlations, it was not a local hidden variable that had been waiting 600 years for its moment. The conspiracy, if there was one, would need to be written into the initial conditions of the universe itself. But there was still a line of objection that had not been completely addressed. The early Bell tests, brilliant as they were, all had technical loopholes, not loopholes in the logic, loopholes in the experiments. Tiny gaps where a determined advocate of local realism could argue that the results did not quite rule out hidden variables. There were three major loopholes. The locality loophole, which Aspect had addressed in '82 with his fast switching. The detection loophole, which exploited the fact that most photon detectors miss some photons, and if the missed photons were systematically different from the detected ones, the apparent violation could be an artifact. And the freedom of choice loophole, which raised the possibility that the measurement settings were somehow correlated with the hidden variables, even if they appeared random. In 2015, 3 independent groups, in the span of a few months, closed all 3 loopholes simultaneously. The first was the Delft group, led by Ronald Hansen at Delft University of Technology in the Netherlands. Their paper, published in Nature in October 2015, was unlike any Bell test before it. Instead of photons, they used electron spins trapped in nitrogen vacancy centers in diamond crystals, 2 diamond chips separated by 1.3 kilometers on the Delft campus. Entanglement was created between the distant electrons using an entanglement swapping protocol. The measurement settings were chosen by random number generators at each location, space-like separated so that no signal could travel between them during the measurement. The detection efficiency was effectively 100% because the electron spins were always there, always measurable, always detected, no photons to lose. The result was a Bell inequality violation with a p-value of 0.039. Modest by physics standards, because the experiment was extraordinarily difficult and could only collect 245 useful trials over 220 hours. That is 18 days of continuous operation to accumulate fewer than 250 data points. 18 days of lasers firing, electronics triggering, random numbers being generated, signals racing across the Delft campus, and diamonds glowing with trapped electrons, all to produce a dataset smaller than what an undergraduate Bell test accumulates in an afternoon. But the loopholes were all closed, every single one, and the violation, modest as it was real. The Vienna group, led by Marissa Justina and Anton Zeilinger, took a different approach. Published in Physical Review Letters in December 2015, they used entangled photons but with superconducting transition edge sensors that achieved detection efficiency above 98%, demolishing the detection loophole. Their result was crushing. A p-value of 3.74 times 10 to the negative 31. That corresponds to 11.5 sigma. For comparison, the discovery of the Higgs boson at CERN was announced at 5 sigma. This was more than twice that. In sigma terms, it is, statistically, one of the most certain experimental results in the history of physics. The NIST group, led by Lyndon Sharm, published simultaneously in the same issue of Physical Review Letters. Photons at telecom wavelengths, detectors 185 meters apart, a p-value of 5.9 times 10 to the negative 9. Another definitive violation with all loopholes closed. 3 experiments, 3 different approaches, 3 countries, all published within months of each other, all arriving at the same conclusion. Local realism is dead, and there is no escape clause, no experimental gap, no technical objection that saves it. And in 2016, the global physics community drove the point home with an experiment that bordered on performance art. The Big Bell test involved 12 laboratories simultaneously across 5 continents, with random measurement inputs provided by over 100,000 human volunteers playing an online game. The volunteers were generating sequences of random choices, and those choices were fed in real time to the 12 experiments running around the world. The idea was to close even the most exotic loopholes, the possibility that random number generators might be subtly correlated with the hidden variables. By using human free will as the source of randomness, the experiment addressed a philosophical objection that no machine-based random number generator could. The Bell inequality was still violated. In every laboratory, with every source of randomness, the universe was not cooperating with local realism, no matter how creative the test. So the foundation under temporal entanglement was now absolute. The entanglement that the Megiddo experiment demonstrated between photons that never coexisted was not some fragile, debatable phenomenon that might be explained away by detector inefficiencies or conspiratorial hidden variables. It was built on the same quantum correlations that 3 independent loophole-free tests had confirmed with overwhelming statistical certainty. The correlations are real. They violate Bell inequalities. They cannot be explained by any theory in which particles carry predetermined properties, and nothing travels faster than light. And this brings us to a misconception that circulates widely and that the documentary needs to address directly. You will encounter the claim, sometimes from physicists who should know better, that quantum entanglement implies that observation or consciousness creates reality, that the act of a conscious mind looking at a quantum system is what causes it to take on definite properties, that consciousness is somehow special in quantum mechanics. It is not. The observer in quantum mechanics is any measuring apparatus, a photographic plate, a particle detector, an electronic circuit, a Geiger counter clicking in an empty room. All of these cause quantum decoherence, the process by which a quantum superposition becomes a definite outcome, and none of them require a conscious mind. The experiments we have discussed used silicon avalanche photodiodes and coincidence counting electronics. No human being was watching the photons arrive. The data was recorded by machines. The correlations were present in the electronic records before any human analyzed them. The von Neumann-Wigner interpretation, which does assign a special role to consciousness, is supported by a tiny fringe minority of working physicists. As Lawrence Krauss once put it, when you hear the term quantum consciousness, you should be suspicious, and you should assume the author is a crackpot, unless proven otherwise. That is blunt, but the point stands. Consciousness plays no special role in any of the experiments described in this documentary. Machines measure, electronics record, correlations appear in the data. The weirdness of temporal entanglement does not require, invoke, or support any theory of consciousness. What it does require is a rethinking of something even more fundamental than consciousness. It requires a rethinking of time. There is a temporal analog of Bell's inequality that makes this point with mathematical precision. In 1985, Anthony James Leggett and Anupam Garg proposed what are now called Leggett-Garg inequalities, published in Physical Review Letters. These inequalities are derived from two assumptions. The first is macrorealism, the idea that a system is always in one definite state, whether or not you look at it. The second is non-invasive measurability, the idea that you can determine the state of a system without disturbing it. Together, these assumptions describe the common sense view of physical reality. Objects have definite properties at all times, and you can check those properties without changing them. From these assumptions, Leggett and Garg derived inequalities that constrain the correlations you can observe between measurements of the same system at different times. If the common sense view is correct, the correlations must stay below a ceiling, just as Bell's inequality constrains spatial correlations. Quantum mechanics violates Leggett-Garg inequalities. The violations have been observed in superconducting qubits by Palacios Laloy and colleagues in 2010, published in Nature Physics, in photonic systems by Gogin and colleagues in 2011, published in the Proceedings of the National Academy of Sciences, and in a remarkable result from 2017, Fu and colleagues used data from the Daya Bay reactor neutrino experiment to demonstrate a violation at 6.1 sigma. Neutrinos, the ghostliest particles in nature, violating the assumption that they are always in definite states as they oscillate between flavors over distances of kilometers. The Leggett-Garg violations tell us something that the temporal entanglement experiments also tell us from a different angle. The common sense view of time, where systems have definite states at every moment and measurement reveals those states without disturbing them, is experimentally wrong. It is not approximately wrong, or wrong in exotic circumstances, or wrong only for theorists who worry about interpretations. It is measurably, quantifiably, statistically wrong, in a way that has been confirmed by multiple independent experiments using completely different physical systems. Bell's theorem told us that reality is not local. Leggett-Garg tells us that reality is not macro-realistic. The temporal entanglement experiments tell us that correlations can bridge gaps in time where neither correlated party exists. 3 different experimental programs, 3 different theoretical frameworks, all converging on the same conclusion. Time, as we experience it, as we intuit it, as we build our understanding of cause and effect upon it, does not work the way we assumed. The assumption that the past is fixed and definite, that systems have properties at every moment, whether we look or not, that measurement is passive observation rather than active participation. Every one of those assumptions has been tested, and everyone has failed. So the experimental case is closed. Entanglement is real, across space and across time. Bell inequalities are violated, with no remaining loopholes. Leggett-Garg inequalities are violated. Particles that never coexisted can be entangled. The past is not as fixed as we thought, but here is where the story shifts from the abstract to the tangible, because temporal entanglement is not just a curiosity for philosophers and foundations researchers. Entanglement swapping, the very mechanism at the heart of the Vienna and Jerusalem experiments, is the technology that will make a global quantum internet possible. The problem is simple. Optical fiber absorbs photons. After about 100 kilometers, the signal is so weak that the quantum information it carries is effectively lost. In classical communication, you solve this with amplifiers. You boost the signal every so often. But you cannot amplify a quantum signal without destroying the quantum information. The no-cloning theorem forbids it. You cannot copy an unknown quantum state. So, how do you extend quantum communication over continental distances? Quantum repeaters. And the core operation of a quantum repeater is entanglement swapping. You create entangled pairs over short distances, maybe 50 or 100 kilometers, and then you use entanglement swapping to chain those short links together into a long-distance entangled connection. Each swap extends the entanglement by one link without any particle needing to travel the full distance. The entanglement hops from pair to pair, swapped along the chain until two particles at the endpoints share quantum correlations over thousands of kilometers. Imagine a chain of stations stretching from London to New York. Station A creates an entangled pair and shares one photon with Station B, 100 kilometers away. Station B creates its own entangled pair and shares one photon with Station C, another 100 kilometers away. Now Station B performs a Bell state measurement on the two photons it holds, one from pair AB and one from pair BC, and the entanglement swaps. Suddenly, particles at stations A and C are entangled, even though they are 200 kilometers apart and have never met. Repeat this process along the chain, swap after swap, and you can entangle particles separated by an ocean. The same protocol that Perez proposed as a thought experiment about the nature of time is also the engineering solution to the most practical problem in quantum communication. This is already being built. China's quantum communication network, the CNQCN, spans over 10,000 kilometers with 145 fiber backbone nodes covering 17 provinces and 80 cities. The Beijing-Shanghai backbone, 2,032 kilometers with 32 relay nodes, became operational in 2017. China's Mischief satellite, launched in August 2016, distributed entangled photons over 1,200 kilometers and enabled the first quantum encrypted intercontinental video call between Beijing and Vienna in September 2017. Zeilinger was on one end of that call. Decades of work, from tabletop experiments in university basements to a live video conference secured by the laws of quantum physics, bounced off a satellite in low Earth orbit. And in March of 2025, China's Jinan, one microsatellite weighing just 23 kilograms compared to Misch's 600, established a quantum link of 12,900 kilometers between China and South Africa. Smaller, cheaper, faster, and reaching further. The technology is not slowing down. Europe is building the EuroQCI, a continent-wide quantum communication infrastructure. Canada is planning the QEYSS-SAT satellite for its own quantum key distribution network. NASA's Sequoia experiment has demonstrated Bell violations from the International Space Station. The technology that Perez proposed as a thought experiment in 2000, and that the Vienna and Jerusalem teams demonstrated as laboratory curiosities, is becoming engineering, becoming infrastructure, becoming the plumbing of a communications network that will eventually be as routine as the fiber optic cables that currently carry the internet. And entanglement is not just powering communication. LIGO, the Laser Interferometer Gravitational Wave Observatory, uses squeezed light, an entanglement-related quantum technique, to push its sensitivity beyond the standard quantum limit. LIGO measures distance changes of less than 1,000th the width of a proton. Think about that scale. The detector arms are 4 kilometers long. The distance change it measures is about 10 to the negative 19 meters. That is like measuring the distance from the Earth to the nearest star 4 light years away and detecting a shift the width of a human hair. Squeezed light, exploiting quantum correlations between photons, is what makes that sensitivity possible. Gravitational waves from colliding black holes billions of light years away, ripples in space-time itself, detected because entangled photons can beat the noise floor that classical light cannot. When Erwin Schrödinger first coined the word for this phenomenon in 1935, responding to the EPR paper, he called it Verschränkung, entanglement. He wrote in Naturwissenschaften that he considered it not one, but rather the characteristic trait of quantum mechanics, not a curiosity, not a side effect, the defining feature of the entire theory. 90 years later, that defining feature is detecting gravitational waves, securing international communications, and enabling computations that no classical machine can perform. In quantum computing, entanglement is the fundamental resource. Every quantum computation that outperforms a classical one does so by exploiting entangled states. Google's Willow chip, 105 qubits, demonstrated below threshold quantum error correction in December 2024. Quantinuum achieved 50 entangled logical qubits with gate fidelity above 98%. Global investment in quantum computing reached $1.25 billion in the first 3 quarters of 2025 alone, doubling the previous year. And entanglement keeps showing up in places nobody expected. In 2023, the Atlas collaboration at CERN, using the Large Hadron Collider, observed quantum entanglement between top quark-antiquark pairs. Top quarks are the heaviest known fundamental particles, with a mass of about 173 times the mass of a proton. They are produced in the most violent collisions humans have ever created, at energies of 13 trillion electron volts. And even there, at the highest energies ever probed, entanglement persists. The quantum correlations that Einstein called spooky, that Bell proved were inescapable, that Perez showed could transcend time, are woven into the fabric of reality at every scale and every energy we have been able to test. And in an irony that Bell and Clauser and Aspect and Perez would have appreciated, the experiments that were once considered career-destroying philosophy are now undergraduate laboratory exercises. Entangled photon sources are commercially available. A company called Q-Tools sells an entanglement demonstrator for teaching labs. Thor Labs sells educational kits. A basic setup costs somewhere between $10,000 and $50,000. Universities like Colgate, Oberlin, and Reed College have their students producing entangled photons and violating Bell inequalities as part of their coursework. Undergraduates routinely achieve violations exceeding 70 standard deviations in these simpler setups. 70 sigma, a result so statistically certain that the probability of it being a fluke is a number with more zeros than atoms in the observable universe. In the 1970s, Clauser was told he was wasting his career on this. Now college juniors do it between lunch and their afternoon seminar. The history of physics is full of examples of forbidden questions becoming routine knowledge, but rarely has the transition been this dramatic, this complete, or this fast. The journey from untouchable heresy to routine pedagogy took about 50 years. The journey from Clauser's 6.3 sigma violation to the Vienna group's 11.5 sigma loophole-free test took 43 years. The journey from Einstein's private complaint about spooky action to entangled photons bouncing off satellites took 82 years. And the journey from Perez's 2000 thought experiment to the Hebrew University confirmation that photons which never coexisted can be entangled took 13 years and outlived the man who proposed it by 8, which brings us, finally, to Einstein's phrase, because the phrase itself is widely misunderstood, and the misunderstanding matters. Spukhafte Fernwirkung, spooky action at a distance. You see it everywhere, in textbooks, in documentaries, in articles about quantum computing. It has become the default shorthand for entanglement, used so casually that it sounds like a technical term. It is not. It appeared exactly once in a private letter from Albert Einstein to Max Born, dated the 3rd of March, 1947, published decades later in the Born-Einstein Letters by Macmillan in 1971. On page 158, Einstein wrote, "I cannot seriously believe in it because the theory cannot be reconciled with the idea that physics should represent a reality in time and space, free from spooky actions at a distance." Einstein was not describing entanglement as spooky. He was arguing that if quantum mechanics required spooky action, then quantum mechanics must be wrong. The phrase was a complaint, not a description, a reductio ad absurdum, not an endorsement. He found the idea so distasteful, so contrary to his physical intuitions, that he used it as evidence against the theory. If this is what quantum mechanics implies, he was saying, then quantum mechanics cannot be the whole story. Bell showed that entanglement was inescapable. Clauser and Aspect confirmed it. The 2015 loophole-free tests sealed it, and the temporal entanglement experiments extended it into a domain Einstein never imagined. Einstein was disturbed by correlations across space. He lived in a world where entangled particles at least coexisted in the same moment, shared the same slice of time, occupied the same now, even if they were far apart. What the Jerusalem experiment showed was correlations across a gap in time where no particle exists at all. Spooky action at a distance became spooky action across a void. If Einstein found the spatial version unacceptable, the temporal version might have driven him back to the patent office. But Einstein was right about one thing. He insisted that physics should represent a reality in time and space. He was wrong about hidden variables. He was wrong about the completeness of quantum mechanics. But the demand that physics describe reality, that it tell us what the world is actually like, rather than merely predicting the outcomes of measurements, that demand has not gone away. It is, in fact, the central demand being made by every physicist and philosopher working on the interpretation of temporal entanglement today. Does the future shape the past? Not in the sense of changing it, not in the sense of rewriting what happened, but in the sense that the physical meaning of past events, whether they were entangled or separable, correlated or uncorrelated, may depend on choices not yet made. If the answer is yes, then time is not what we think it is. The flow from past to future, the sense that what is done, the feeling that the past is fixed and the future is open, all of this may be a feature of our experience rather than a feature of reality. The block universe may be the truth. Past, present, and future, equally real, equally connected, equally susceptible to the correlations that quantum mechanics insists are there. If the answer is no, if the correlations are artifacts of post-selection, then the mystery is different, but no less deep. Why does the formalism of quantum mechanics produce results that perfectly mimic backward influence? What is the universe doing when it generates data that looks exactly like the future, reaching back to shape the past? If the future is not actually reaching back, Perez, in his characteristic precision, gave us the right word: mimic. The results mimic retroactive influence. Whether they are retroactive influence is a question that physics has not yet answered, and may not answer until we understand something about reality that we do not currently understand. But the experiments are done. The data is in. Photon 1 was born, measured, and destroyed in a laboratory in Jerusalem. Then Photon 4 was born. It never met Photon 1. It never occupied the same moment of time. And yet, in the records, verified by 5 independent tests, those 2 photons are entangled. There is a road at CERN named Route Bell. There is a street in Belfast's Titanic Quarter called Bell's Theorem Crescent. There is a quantum satellite orbiting the Earth named Mikius. There are undergraduates in teaching laboratories casually violating inequalities that cost Clauser his career and Bell his reputation. There is a building at the Hebrew University of Jerusalem, at the Reika Institute of Physics, named after Giulio Reika, the father of theoretical physics in Israel, where 6 researchers demonstrated that time does not work the way any of us thought it did. And in a cemetery in Haifa, there is a grave belonging to a man who was born Aristide Pressman in a small town in southern France to parents who had fled Eastern Europe looking for safety and did not find it. A man who hid from the Nazis as a child, who was trained by Einstein's collaborator, who spent his career at the Technion proving things about quantum mechanics that made other physicists uneasy. A man who, when a reporter asked if quantum teleportation could teleport the body as well as the soul, replied, "No, not the body, just the soul." A man who wrote in a sole author paper in the year 2000 that entanglement could be produced after the entangled particles had been measured and may no longer exist. A man who titled his memoir after a Kipling story about a cat that walks alone, because he had spent his life walking alone through ideas that others were not ready for. He was right. The experiments proved it. He was not there to see them. The outsiders made this field. Bell, working on quantum foundations as a hobby because CERN would not fund it. Clauser, told it would destroy his career. Aspect, warned by Bell himself to secure a permanent job first. Pears, a refugee child who grew up to propose the most unsettling experiment in quantum physics. Every advance in this story came from someone the establishment told to stop. The question they forced on physics is still open. What is time? Is it a flow from fixed past to open future the way it feels? Or is it something else? Something more like a landscape where all moments exist together, connected by correlations that do not care about the order we experience them in. We do not know. The experiments have outpaced our stories. We have data that our best interpretations disagree about, results that our best theories cannot unanimously explain, and correlations that reach across gaps in time where nothing exists to carry them. We are, as Wheeler might have said, participants in bringing meaning to phenomena that resist easy categorization. The conversation between experiment and interpretation has been running since Einstein wrote his letter to Born in 1947. It has been running through Bell's lonely evenings at CERN, through Claus's basement at Berkeley, through Aspect's optical bench at Orsay, through Perez's office at the Technion, through the fiber optics of Vienna and the crystal labs of Jerusalem. It is not finished. It may never be finished. And that is not a failure. That is the sound of physics doing what physics does, pushing against the boundaries of what we understand, finding those boundaries further out and stranger than anyone expected. But whatever the answer turns out to be, it will come from someone like Bell, like Clauser, like Aspect, like Perez, someone working on the question everyone else says is settled, someone willing to look where the establishment says there is nothing to see, someone who knows, the way Perez knew, that unperformed experiments have no results, and that the only way to find out what the universe is doing is to go into the laboratory and ask.